Hello and welcome to today's session. Today's session will discuss about skewness, kurtosis, mean absolute deviation and coefficient of variation. So in the last class we saw some central tendency measures like mean, median, mode, quartile, interquartile range. So today's session will discuss more about the shape concepts, right? So like skewness and kurtosis. Skewness, kurtosis. Kurtosis is also called as moments. Basically, these two concepts of shape is used to indicate the symmetry or asymmetry of the representation of your data set. So coming to skewness. So skewness is basically a measure of the degree and direction of symmetry. So it's a measure of direction as well as degree of symmetry, and it is also called as third order of measure. So the last session we saw that mean, median, mode, they are the first order measure. The quartile, deviation and interquartile range is the second order, and shape like skewness and kurtosis, these are third order of measure. So basically, if a skewness is 0, we call it as an ideal normal distribution. Okay, but if you have a 0 value of skew, that means it's an ideal distribution, but normally that doesn't happen. Most of the data sets will be not perfect, right? Most of the data sets that you collect, either it will have very high values at one end or extremely low values at some ends. So if the data set is having far higher values, then you say that it is skewed to the right. If the data set is having far lower values, then you say that it is skewed to the left. So look at this diagram. So in this diagram, right, this we call it as negatively skewed, because what happens here is, in negatively skewed, you can observe that the tail is much on the left hand side and you have high values on the right hand side. The reverse is positively skewed, where you have tail which is going on much deeper on the right hand side and you have very high values on the left hand side. This one is a perfect symmetry, so we call it as a zero skew, or it is a ideal normal distribution, right? Because you can see that the curve is symmetrically distributed on both the sides. But most of the data sets are far from normal, right? Most of the data sets, when you're working in machine learning, you will see that either they will be negatively skewed or positively skewed. So coming to the skew concepts again. So if suppose I say it is a normal skew, skew is 0, or if I say it's a normal distribution, then there are not much of outliers, right? But when you have a positive skew or a negative skew where you have extremely low values or extremely high values, then mean, median will also get affected. Okay, so suppose in case of a skew, what happens is, normally when there is a skew in your data, median will not be equal to mean. In your positive skew, mean will be much more compared to the median, and in a negative skew, median will be much more as compared to a mean. So actually there's a relationship between skew and mean and median, which is represented by the Pearson 2 skewness coefficient. This is the formula. Okay, so this formula is called as the Pearson 2 skewness coefficient, where the relation between skewness and relative size of mean and median are represented. So this mu is this is the mean value. You subtract it with the median, multiply that by 3 and divide it by standard deviation. So that represents, or this actually formula will give the relationship between skewness and mean and median. Now let's say I have some n observations like this, x1, x2 up to xn. So skewness, this is how you calculate. For each value, you subtract that with mu, that is the mean, cube, take the cube of that, divided by standard deviation cube, and repeat the same thing for all the values in your data set and take the summation of that, and that entire thing you have to divide by n. So that will give the skewness. Okay, now coming to the next one, kurtosis. Kurtosis is also used, just like skewness, this is also used to indicate the peak of the data, right? So this diagram represents the skewness. This is positive skew, as I said, this is negative skew, and this is a symmetrical distribution. This is kurtosis, right? This is the negative kurtosis, this one is the positive kurtosis, something in between, which we call it as a normal, we call it as mesokurtic. So what you observe here is, if the data is high peak, so for example there is a high peak here, we call it as a positive kurtosis. If the peak is lower, we call it as a negative kurtosis, right? Also you must observe the tails, right? In negative kurtosis, the tails are much longer as compared to the positive kurtosis. and this is what we call this as mesocurtic, which is actually called as a normal distribution. So if you're in statistics, this is a very important concept. Normal distribution is nothing but bell shape, which is always preferred, right? Bell shaped curve is a normal distribution, it's an ideal distribution, and it is always preferred. This is what we see in dotted lines in both the diagrams, is a bell shaped curve. Now why it is preferred is you can see that it is symmetric on both the sides and there are not much of outliers, right? There's no outlier data, so that's why bell shaped curve is the most preferred distribution. Now as you can see here, in positive kurtosis it has a very sharp peak and the tails are not longer as compared to the uh, normal distribution. In negative kurtosis you can see the peaks are much flatter and very lighter tails. So suppose in terms of formula I have some n observations like this. The kurtosis is calculated like this. For each value you subtract with the mean, take the fourth power of that, divide it by n, that is the total number of observations, do the summation and then divide it by n, then divide this entire thing by fourth power of standard deviation. So that gives a kurtosis. The next one is mean absolute deviation. Now mean absolute deviation is also one more dispersion measure, and this is also very robust to the outliers. And how do you calculate this is, absolute deviation is it just subtract each value in your data set with the mean. So that will give the absolute deviation. Then take the summation of that. For each value you subtract with mean, take the summation of all of that, then divide by n. So that gives a mean absolute deviation. So x minus mu is the absolute deviation. Divide the summation of that with n gives the mean absolute deviation. The next, coming to the coefficient of variation. Now this is a very important parameter which is normally used to compare data sets with different units. So how do you calculate coefficient of variation is, take the standard deviation divided by mean into 100. So that nothing but gives the coefficient of variation. Now this is a very important measure when you want to compare data sets with different units. So that was about for today's session. So today's session was a quick revision of the kurtosis, skewness and mean absolute deviation and coefficient of variation. Now the one question which will come into mind after studying all these topics is, why do you have to do all this? Why do now machine learning is all about statistics, all about you do the analysis, all about understanding your data sets. To understand your data sets you should be able to map these concepts to your data set. You should understand the outliers in your data set. You should try to achieve right normal distribution, not achieve, ideally at least reduce the skewness, at least reduce the kurtosis, so that the number of outliers are less. So these are all measures of how good your data sets, which will definitely affect the performance of your algorithm. So thank you so much. In the next session we'll meet again for the last concept of special univariate, called as special univariate plots. So thank you so much, and please subscribe to the channel. Thank you.